Hello everyone, my name is Partha Debnath. I am a doctoral candidate at the Hong Kong Polytechnic University in Hong Kong, and I'm working under the supervision of Dr. Tak-Ming. Today I'm going to present on the topic Enhanced Composite Behavior of CFST with Blind Bolted Connections under Tensile Pull-Out Tests. So I have subdivided my talk into several parts like the introduction, the background, about the motivations about my study, the modeling aspects, observations, and future experimental investigations. So before I move into the subject, let me first introduce briefly about the CFST, or the concrete filled steel tubes. The concrete filled steel tubes are very common worldwide for construction of high-rise structures, and this is because of its superior strength, higher ductility, aesthetics, better fire resistance, and less vibration sensibility. Also, because of its capacity in resisting higher loads uh, in post-steel behavior, and also because it does not require any formwork, the construction of CFST is much faster as compared to other RCC structures. And the bolted connection, which is also a type of connection like the welded connection, is much easier and faster in fabrication as compared to the welded connection, and because it requires only semi-skilled labor, the 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 fabrication cost of bolted connection is also lesser than the welded connection. And as it is understood that the bolted connections can be easily replaceable, whereas it is not so easy to replace a welded connection. Now, when it comes to the blind bolts, the blind bolts are the special type of bolts which are used to connect a open section beam with a closed section column. Now the like for example, this is a closed section column and here is a single bolted connection. Now for a single bolted connection, uh, if the column is a closed section, you cannot access the inside of the column. Therefore, we use the blind bolts. But the problem with the bolted connection is that it has severe slippage problems and column surface deformation. I mean, this is the column surface, and because of the tensile or the shear loading, this surface of the column has severely deformed in existing findings, and it has a low moment resisting capacity, because when we build a structure in seismic regions, we always want the structure to behave in a rigid way or in a semi-rigid way. But most of the uh, bolted connections are considered as pin connections. It also has less stiffness and rigidity. The bolt capacity is not effectively used, and the concrete contribution in CFST is not pronounced. What I mean by concrete contribution in CFST is not pronounced under shear and moment load is that when the concrete filled steel tube is under compression load, the contribution of the concrete is pronounced. But when it comes on the shear or moment or any tensile load in a connection, the concrete contribution is not very significant. So we are trying to address these problems. But in the recent past, there has already been some studies in countries like Australia, Hong Kong, and in UK, that this is a normal blind bolt, and this has been fitted or welded with a bent bar which will act as an anchorage into the concrete core. And this has also been proposed in Australia, where the normal blind bolt has been fitted with an extended shank and fitted with a headed nut. So these are some modifications. Also in Nottingham, University of Nottingham, they have modified the Lindapter hollow bolt with the extended or a longer shank with a headed nut. And this type of modifications has actually performed well, where the behavior of the connection has shown improved strength, stiffness, ductility, rotation capacity, and energy dissipation. But there is still some more work to be done, and that's where our motivation lies. So the reason behind further carrying out this work is because the test data available is still insufficient to conclude for any design guidelines of the extended hollow bolted connections. and the holistic approach for different parameters were missing, like the failure mode of such CFST, EHB or bolted connections will depend on the grade of the concrete, the tube thickness, the embedment length of the bolt. I mean, like these are the various embedment lengths of the bolt, the grade of the bolt, the diameter of the bolt. So this holistic approach of the connection needs to be investigated. And how does a single bolt and the group bolt behave? I mean, is there any significant difference in the behavior of group bolted connections? Also needs to be investigated. And later, the component behavior also needs to be established to predict any connection behavior. Now, for the current study, we are more concentrated into the behavior of single bolted connection. Then we have done some numerical validations from existing studies, and then we have conducted some parametric studies which we have reported in this work. The existing tests we have included for validating our numerical models are from Australia, UK and Hong Kong, where researchers have used the headed anchored blind bolt. This is the experimental setup. This is the extended hollow bolt. This is the experimental setup, and this is the experimental setup for using slip critical blind bolt. So we have used 3 different types of blind bolts to validate our numerical models and gain a confidence on our numerical modeling results. So the modeling aspects, first I would just like briefly give what are the modeling aspects we have considered for our FE models. The model proposed by Yoon and Gardner has been used to model the steel. The model proposed by Tao and Wang has been used to model the concrete, and the bilinear function proposed by Hillerberg has been used to model the concrete tensile stress in the commercial software Abacus. And here I have just briefly mentioned about other selection of my materials, mesh size, boundary conditions, contact surface behavior, and other local imperfections, Poisson's ratio, all these matters which are, I think, don't have to discuss much on this matter. And this is how I have modeled my extended hollow bolt. This is the extended hollow bolt, and this is how the numerical model looks like in Abacus, and these are the interaction surfaces. Now, as one can imagine that there are so many interaction surfaces with the sleeve, with the bolt components, and then the bolt component with the concrete surfaces, the steel tube with the concrete, and the stub plate with the bolt and the concrete. So there are numerous interaction surfaces, and we call it surface to surface interaction. And now in Abacus, we have to be very careful in modeling these interaction surfaces, otherwise these can lead to non-convergence. Therefore, I have used the Abacus explicit to achieve the convergence for these such type of complex numerical models. As you can see, these are the FE validations, and the solid lines represents the experimental results and the dotted line represent my numerical models. And if we compare all these experiments which have been collected from various authors, we can conclude that the numerical models are in good agreement with their experimental counterparts. Also, you can see how the failure modes of the bolts, the hollow bolts, and the failure modes of the concrete are in very similar as compared to the experimental failure modes. So as a result, we can conclude that the numerical models are in good agreement and can be well carried forward to do further parametric studies. For the parametric study, we have considered the extended hollow bolt and not the slip critical blind bolt or the headed anchored blind bolt. So we have considered the extended hollow bolt, and this is the blind bolt, and this is the CFST or the concrete filled steel tube. This is the steel tube and the confined concrete. This is the rigid stub plate, and this is the direction of the load. Just to mention here that we have applied finer mesh in the connection region and coarser mesh away from the connection region. So there are several parametric studies which we have carried out, and the parameters includes the length of the bolt embedment, the grade of the bolt, the grade of the concrete, the steel tube thickness, and so on. So if we consider prominently the bolt embedment length, we can see that the bolt embedment length, as the bolt embedment length has increased, there have been an increase in strength and stiffness of the connection. So this is the normal hollow bolt. You can see the strength and stiffness is very less as compared to a bolt which has longer embedment length. So if we calculate the bolt design strength as per Eurocode 3, we can see that a higher bolt embedment length has been able to give higher strength and stiffness of the connection, but always may not be we may not always use a higher bolt embedment length, because the higher bolt embedment length may lead to the failure of the bolt. So we may not actually want the failure of the bolt, because we want the bolt to be a stronger component. So a proper combination of high strength bolt, concrete and steel tube thickness needs to be established. And then we have you can see the failure in the concrete. This is the normal hollow bolt. The failure in the concrete is very less, I mean the damage in the concrete is very less, but when it comes to extended hollow bolt, you can see the concrete damage. This actually shows the concrete contribution in enhancing the strength and stiffness of the connection. These are the stress distribution in the modified bolts, so which shows that the connection has been influenced by the capacity, by the embedment length of the bolt. And these are other failure modes, other behaviors. The concrete contribution, the encouraged tube wall contribution can also be observed from this behavior. We have also mentioned how the grade of the bolt is significantly affecting the behavior. You can see the grade, this is grade 8.8, this is grade 10.9. When it comes to concrete grade of C40, you can see significant concrete damage, but when you use a higher grade of concrete of C70, you can see the bolt is necking. But actually again, this may not be the preferred failure mode. So from this we can see some observations which you can make, or which you can briefly make, is that the extended hollow bolt can significantly enhance the concrete contribution, and this strength enhancement can be up to 2.5 times, which is very high. Then the concrete crushing is followed by tube wall yielding, may be regarded as the preferred failure mode. The grades of concrete of C40 to C50 may be used as infill concrete, because beyond C50 the influence is not significant. The connection stiffness is influenced by B/T ratio for hollow bolt connections, but for extended hollow bolt connections, the stiffness is influenced by B/T ratio, concrete strength, bolt diameter, bolt embedment depth. And the generated FE models can be used to predict the behavior of EHB CFST connection. Apart from the numerical studies, we are also conducting extensive experimental investigation at the Hong Kong Polytechnic University, and we are going to report the failure modes and their behavior along with component model in the coming days. So this we are going to report in our coming experimental findings in our coming research papers. So please stay tuned, and that's all from my side. Thank you, stay connected and stay safe. For any other further information, please feel free to contact in my email address. Thank you.